UBC CS 532W. My name is still Frank, and this is still Probabilistic Programming. So we're in the middle, I think this is lecture 8, is that right? Lecture 8 of 28, I think, not that I'm counting. And this is in the middle of the lecture slides 7 and 8. I think the first thing that I should announce, there is like some announcement. If you have looked at homework 2 or downloaded the slides and followed them at home, there are updates to the slide deck, and there are significant updates to homework 1, the text online and the support code. So it has been improved, robustified, and all sorts of stuff. If you stick around afterwards, I think I might have Barend prepare to show his screen and maybe take you through the support code just a little bit so you see what's there. I could do the same. And my congratulations and thanks to Barend for actually and Christian for putting together what I think is going to be something that makes the second homework super awesome and very accessible. So, cool. So where did we leave off? Well, last time we kind of spent a long time. What did we talk about last time? Yeah, the state of probabilistic programming, that sort of stuff. Where we left off was the design of a probabilistic programming language without recursion, and we basically got to the syntax for a language where we said there's variables, constants, procedures, and then a bunch of possible expansions, constants, procedures, special forms, if and let, and function procedure application, primitive function application, sample, observe, definite, so on and so forth. So you can think about this as like a kind of an abstract syntax-driven intermediate representation language, particularly if you don't like functional programming or Lisp. And I think we got here where we looked at this program, and I had you stare at it a little bit. Hopefully you've looked at the book and are a little bit more up to speed, have some questions maybe. And I said that this program represents a linear regression, a Bayesian linear regression model. Oh, wait, actually, there's Jason. Okay, I was gonna have everybody make fun of Jason for not being here, where the uncertain quantities are slope and intercept, and they're sampled from some prior. And then there's a whole bunch of ugly nested let statements in which some data, x, y pairs, are fed to a function called observe data that takes the unknown parameters, constructs the line, basically the estimate, the target estimate by multiplying x by the slope, adding the intercept, and that's the function evaluated at fx, and then at x, and then observes a normally distributed quantity with standard deviation 1 to take value y. So we've got input, output, input, output, input, output, input, output, input, output, 5 different input-output pairs. And this program represents the posterior distribution over the slope and intercept given the observed input-output pairs. And since I've switched over to a better presentation mode rather than Keynote, I will have to manually draw the video that you that you saw last time, which was basically a graphical representation of the posterior distribution of the parameters of the line. Okay, fine. I think this is probably the most hideous slide design we'll have for the entire term, so bear with me and we'll just go through this because it's important to understand the underlying language even before we get to its semantics, which we will start Tuesday. And this you do need to pay attention to, because the stuff we're talking about now is really going to help inform how you deal with homework 2 and then subsequently all of the homeworks. So getting this is pretty important. So a constant can be any primitive data type, such as a number, string, or Boolean, a built-in primitive function, such as plus, or convolutional neural network, or something like that, or any other data type that can be constructed using primitive procedures, such as lists, vectors, maps, or distributions. So basically, like I said, there's an underlying language whose meaning we agree upon, and basically C is going to be a value in that language, or corresponds to a value in that language, which again could be a number, string, Boolean, or even a built-in function, right? Please do note the fact that, and this is something that is easily overlooked in the book, despite the fact that we tried to, or I have tried to make this clear throughout. Everything that we talk about in the underlying languages can be deep neural net languages with very, very large, very powerful primitives, RNN primitives or CNN primitives or whatever. So values in the language can, so in other words, values, the things that these constants C can take on, can and will include lists, vectors, maps, scalar strings, distributions, symbols, and more. Okay, so this is a little bit different to standard languages because you don't pass around distribution valued objects, but our language is going to allow us to pass around distribution valued objects. Okay. A variable v is a symbol that references the value of another expression in the program. That's cool, right? A let form, we already saw this, a let v e1, e2 binds the value of expression e1 to the variable v, which then can be referenced in expression e2, which is often referred to as the body of the let expression. Okay. An if form, what is the meaning of an if expression is if takes the value of the second expression when the value of e1 is logically true and the value of e3 when e1 is logically false. Again, we'll call the e1 the predicate, e2 the consequent, and e3 the alternative. Function application, f calls the user-defined function f, which we also refer to as procedure, to clear up Naomi's question, clear up Naomi's question from last time, with arguments e1 to en. And here the notation e1 to en refers to a variable length sequence of arguments, which includes having no arguments. In other words, the case for a procedure call with no arguments. F. And a primitive procedure application, C calls a built-in or primitive function C, such as plus or CNN or something like that. The two unusual forms are sample, which is not so unusual, but these two will eventually be, so the language so far is side effect free, which is to say that you can take any of the expressions and put them in the place of, like, basically replace a value or a variable bound to the value of an expression with the expression itself, and those two things are equivalent, which is very interesting and cool, something about lists. That is not going to be true about sample and observe, because sample has a side effect of changing the random number seed, basically, and observe will have other side effects. So these are the side effectful operations. So sample form represents an unobserved random variable. It accepts a single expression e, which must evaluate to a distribution object. So this is an untyped language, but untyped languages are kind of a lie because they do what's known as runtime type checking, basically by failing if the types don't match what is required by the called functions. If people know about type systems and want to talk about type systems for probabilistic programming languages, that is well in the realm of final project material. It accepts a single expression which must evaluate to a distribution object and returns a value that is a sample from this distribution. Distributions are constructed using primitives provided by the FOPPL, this language. For example, normal 0, 1 evaluates to a standard normal distribution. An observed form, observe e1, e2, represents an observed random variable. It accepts an argument e1, which must evaluate to a distribution, and conditions on the argument e2, which is the value that the random variable takes. Okay? So this is basically a node in a graphical model, and this is a shaded node in a graphical model. Okay. So this language is a is a big little language, but being a little language, it has some interesting restrictions that are worth thinking about from a what can you represent point of view. Is you'll notice the language has no I/O facility whatsoever. And for people who are not computer scientists or aren't used to this notion, this is potentially problematic. Like, what can you do besides compute a value, right? Yeah.
I have a question. What does I/O stand for?
Oh, awesome. God, we should really come up with like there should really be paid positions in graduate courses for people who ask helpful questions. It's like almost as important as a TA. So I/O stands for input, output. So if you look at the language, you just go back to the language. If you stare at this, hopefully you have looked at this, right? There's literally no way to input data, right? I mean, you could argue that there's you could be cheeky and have a primitive operation be like read CSV or something silly like that. But yeah, that would be a bad idea. So basically, data must be inlined in this language as code. Okay? So when you see the examples in the FOPPL, the code will the data on which you'll condition, i.e. the denotation of the distribution, if it is a conditional distribution, requires closing over the data. Okay? And that's for those of you who have done 340 here, not an unreasonable thing to think about, particularly when you think about non-parametric function estimators, where we talk about that as estimating a function which closes over the data. I'm guessing that, James, you remember that.
Oh, of course, yep.
Thank you for reinforcing the excellence of our 340 pedagogy. How about you, Greg? Do you remember that? You've been TA for 340 like 800 times.
I have no idea what this closing over the data means, actually.
Okay, so closing over means basically that the function itself has the data in it. Like the body, the description of the function actually has data in it, in the manner that we'll talk about, I think, not here, but when we were looking at the description of this posterior distribution, right, over the parameters of a linear regression model, the data is here. The denotation closes over the data, right? It hides the data when denoting the posterior distribution of slope, intercept, given data.
So you can only use this definition for this particular problem, and if you can't like just say I've already written the code out, I can't just copy and paste it over. You have to input all the data all over again.
Okay. This is okay. Yes and no. Okay. So yes, this program denotes, and I think Ryan was so bold as to be very, very nice and actually say that the last lecture, despite my empty and hollow feeling after giving lectures every time on Zoom, that he actually enjoyed and got something out of the last lecture. That made me feel really, really good. But so remember what I mean when I keep using the word denote, right? Which means that this is the way we write down a particular distribution, right? So a particular distribution, when you are conditioning on some data, like the data is part of the specification of the distribution. So indeed, if you want to specify a different distribution, you indeed have to put different data in. And then the program will denote a different distribution. We haven't, not even one time yet, talked about how to actually computationally characterize that distribution or evaluate this program. All we're saying is that this denotes some distribution, and here it denotes a conditional distribution conditioned on data which is closed over, i.e. hidden by the syntactic, hidden by the expression, within the expression. Now, if you wish to, and this is worth thinking about as well, it's kind of an interesting thing to think about, your point is really leading to two things. One is one of the reasons why you actually want a higher order probabilistic programming language, so that you can do I/O. And as soon as you do I/O, then you're in a world of hurt, basically, unless you have very special I/O mechanisms. That's number one. But number two, is it such a problem that you have to inline the data?
Well, if you have 5 million
Yeah.
images in your data set, then
Sounds pretty unnecessarily labor intensive.
Is it labor intensive?
You can write a computer program to inline the data for you, right? Like, that's not forbidden in the language, right?
Indeed. So Berend has come to the rescue despite learning at the same time as you all, basically, right? So you can write a program to write this program. What's the problem with that? There's nothing labor intensive about that. You just, I mean, you copy all of this and you copy that line, and then you write a little program generator that literally just makes these lines. And does that really cost more than having the data on disk, Greg? No, right? It's the same.
Well, the program that's supposed to do the writing would, in some sense, require twice the memory unless you do multi-threading heavily.
Multi-threading has nothing to do with it, but yes, if you were to literally write out this program in the way that Berend suggested, then yes, to hold it, you would have two copies of the data, and that would cost a constant amount of representation. But this storage, but this thing represents something different than the data. It represents the posterior distribution.
I have a question.
Awesome.
Because we're not allowed I/O operations, then how do we get like the slope and the intercept in this case? Like,
great. We're in the position of high confusion. Again, we haven't said how we're going to computationally characterize this thing, right? We're just saying what it represents, right? So we'll get to computational characterization pretty soon. Okay, cool. So no I/O, data must be inline as code. No higher order functions. So this is to say that functions, there are no values which are functions. So if you're familiar with lambdas in Python, or functions is first, you can pass functions around. Who doesn't know what a first class function is? Just to, okay. Who does know what a first class function is? Can somebody else say it in a different way than I just did that makes it easier to is that a no, Adam? You refuse to say it in a different okay, so you could imagine writing code that looks like this. I don't know why that parentheses is so large. You could imagine writing let f be fn x times x. Okay. F of 7. Oh my God. Switching. F7. Okay. So in this particular case, this would be a inline function, right? I guess in the FOPPL case, we do this defin f x times x. This is not a particularly elucidatory example here, unfortunately.
So Frank,
Yep.
does it mean that having no first class functions means you can't pass a function to a map, right? Would that be kind of an example you might want to use?
Yes, but that requires everybody knowing what map is and what a first class function is, because you have to know what a first class function is in order to have. So you basically, the point is you can't like, here is a variable, and the value of this is actually a function, right? And I've assigned the variable value f to a function name, to an actual function object, right? So in functional languages, those variables can take the value of a function, which is cool, right? But this is not allowed in this FOPPL. This is actually syntactically restricted, which is to say that if you'll notice, the only place, so we've actually called out, and this is like, these little languages look like they're sort of really easy to design actually, but it took a very, very long time to actually design this just right. This little f right here only occurs in two places, here and here. It cannot actually ever appear anywhere over here or in an assignment anywhere or something like that. There's no way to do that. So this language is syntactically restricted from having first class functions. I guess, I don't know if there's a way to look ahead really quickly to the FOPPL. I don't think there is, but when just to presage something, the FOPPL will actually end up being a higher order probabilistic programming language, which has first class functions, will end up being a simpler language. In other words, it'll have fewer special forms. It will not have a form like this. It won't even have a let form. It will only have an fn form, which will allow for functions to be values in the language. And then when you have that form, crazy things happen, okay? But just hold your hat on that one. Cool. So no passing of functions. There are no recursive calls. Now these we cannot restrict syntactically. It's not actually really possible to do that. So this is something we just have to trust you not to do and to make compile time restrictions via scoping. So the first thing is the user-defined functions both can only call previously defined functions and also can't call themselves. So this is something that the compiler can stop, but we can't stop syntactically. So the point is that this defin form, this E cannot refer to this symbol F. Moreover, whatever is in this E cannot refer to any functions declared after this. So if there's a sequence of defins, they can only refer to the names of functions before. And so long as that's true, no recursion is possible. And recursion, even for those of you who don't necessarily write recursive programs or aren't super familiar with recursion, recursion is a really good way to get yourself into unbounded variable cardinality models. So we have to restrict that at compile time. Now, the consequence of having made all of these assumptions, which we've made very explicitly, and other languages have sort of inadvertently come to, is that provided that all of the primitive functions halt, right, then all computations halt. Just to say that there's only ever a finite number of steps that any of these computations can take, because there is no general recursion. And there's no I/O which would allow unbounded numbers of operations on a potentially unbounded amount of data being input. For us, the critical implication is that this little teeny tiny language with these restrictions, because all computations halt in a finite number of steps, because they halt, means that no matter what you write, no matter what expression you write, the number of random variables in denoted by any expression is always finite. Okay, cool. And like I said, other languages have sort of inadvertently come to these restrictions. Languages like Bugs and Stan are actually first-order probabilistic programming languages. So in essence, are TensorFlow and PyMC3. Okay. Cool. Questions at this point? Okay, cool.
Sorry. So for constants, they cannot be they cannot be user defined, or can they be?
Constants?
Yeah.
Oh yeah, the constants are values, are fixed values in the implementing language or in the language, in the underlying language. They're primitive. 7.
So users cannot define them.
They that's correct. If what you're saying is what I think you're saying, then that's correct. Users can only define them in the sense that they define the underlying implementing language.
I'm guessing the variables are not immutable either.
So here, you don't actually have to think about this, but there is something that is worth thinking about here. So Payman's question is about the data structures used to represent values in this language. The reality is that you can think about a language like this as a pass-by-value language. So the immutability is an implementation concern, not a semantics concern. So if you want to have a pass-by-value language that is efficiently implemented, you want the underlying data types to be immutable data types. But maybe I can do a little example here. The most important point of any expression that doesn't have these things in it in the deterministic language, which we'll get to in just a second, but is that anytime you have an expression, vector 7 to conj 13, right? This is exactly equivalent to the value. This is exactly equivalent to the value. So if you use this anywhere, like let z be plus 8, 9, and whatever, return times z. This is equivalent to let, we can just, let blank times plus 8, 9 plus 8, 9. Okay.
I guess my question is more along the lines of, if you have 2 assignments for z in your let statement, is this something that that is semantically
you cannot.
valid? So is it the compiler that catches
you cannot. It's not possible. There's only one binding. That's actually really important.
So if they were nested, is it just like you do the scoping so that the closest one within the span is what's
Correct.
taken. Okay, cool. So then they are immutable. It's just that it's not explicitly set per se.
Again, you should think of them as pass by value, but an efficient implementation would be immutable. And the nesting of names has nothing to do with immutability at all. That only has to do with lexical scoping, right?
Thanks.
Yep, good question. Thank you, Payman. Okay, cool. I guess I didn't pause quite long enough, so maybe I'll pause just a little bit longer here and hope for some more questions, because those are all really good questions. Naomi, I didn't mean Naomi, I meant Emma. Don't tire of asking questions when there are things that are troublesome. I know that I used a bunch of terminology that was kind of wacky. It's all in the book. Hopefully you read in the book, but you know, we're like, it'll come in. It'll make sense as you do the homeworks and that sort of stuff. If the terminology doesn't all land right now, it's a fair amount of jargon, but. Mia? No? Namrata? No? Okay, cool. Speaking of, the language itself is a little bit, it's a small language. So this is a cool word used by the programming languages community, sugar, okay? It's like nice stuff to have. There's some sugar that we're going to talk about so that you can actually read the programs that I put in front of you. You can read the homework programs and understand what's going on. So in the FOPPL, we treat this underscore symbol as a special form of syntactic sugar, which at compile time is expanded into a so-called fresh variable, okay? And a fresh variable is simply a unique, never ever duplicated, always different variable name.
I'm actually curious about this. Can you clarify like why that is specifically so important? Like why it's never been used before? Is that just for the sort of stuff that goes on in the background with keeping track of likelihoods and stuff, or?
Yeah, so this is fresh variables are going to be used all over the place in our operational semantics and in naming random variables and in addressing schemes later on and so on and so forth. So here, this is really like a foreshadowing thing to talk about it here, because the necessity of fresh variables it's not necessary on the surface form at all. What it is necessary to deal with sugar, so we can actually name variables and have them be syntax compliant, but without stepping on any variable names that are already existing in the program or otherwise scoped. But it will become very, very necessary when we're talking about like the translation rules and addressing schemes later on. Okay.
Yeah, gotcha.
Awesome. Was that Naomi? Yeah.
So do we see the variable name? Because you said it's at compile, it's expanded. So when we're writing, do we?
Yeah, so what I'm saying is many languages have this facility for users. Like it is syntactically required that a variable name sit here in order for you to write a syntactically valid FOPPL program, right? But as a programmer, you have no use for that variable, you just say, blank, I don't care. I don't care what its name is. I'm never going to use it. I can't access it.
So that happens often, that we have a variable and we just give it a name because we have to, but we don't ever refer to it?
Yes, that will happen quite a lot. And there'll be some examples in just a little bit of where this happens inside the compiler. But when you're writing code, there are certain circumstances, in particular, when, for instance, you have a sequence of observed or something like that. You don't, if you want to put an observe in a let, it doesn't even have a return value. So you're not going to bind it to anything. So whatever, right? Okay. So there's usually some sort of gensim primitive in a language. I believe that it's hard to say because we haven't completely designed all the homeworks for the course this year yet, but I don't think you'll have to deal with gensimming yourself. Okay, so the first thing that sort of combines Payman and Naomi's question into one is that, Payman was asking, what about having multiple bindings in the same let block? Well, those are syntactically disallowed, but for writing programs, you definitely want to be able to write let something, right? So we introduced Syntactic Sugar, and this is going to be relevant because the programs that you see in the homework will be sugared programs. They will be written in compact forms that use these sugar constructs that are then desugared for you. The only person who really should actually write the compiler in this, as far as I can tell, is Ryan, and we can talk about why Ryan should write this compiler at some point. But the desugaring will be done for you, but you should be aware that it's being done. And in particular, what desugaring does is it says, before we do any sort of compilation, before we do any sort of evaluation, we're going to remove forms that look like this and replace them with semantically equivalent forms that look like this. So if you see what happens here, we have a bunch of variable names and we have a bunch of expressions, okay? And we already know, you've already seen a couple of times, that the value of a let expression is the value of the last expression in the let block, okay? That means we can do a bunch of stuff that has, for instance, side effects, like observing things, but then you actually want the return value of the program to be something, right? So, cool. So what do? Well, we say, let V1 be E1. Great, that's the first thing. But then we say, let V2 be E2, adding another parentheses, so on and so forth. And we keep going until we've consumed all of the V's. And then, and here we put in some sugared code that then gets desugared by the compiler. Let blank, we don't care what the value of this is, be the value of En plus 1. Let blank be the value of En plus 2. So on and so forth, all the way down to the very end. Okay? And then the value of this entire nested set of let blocks with only one binding per each let is En, which is exactly this guy right here. Okay, Ryan is showing signs of being perplexed. Or maybe I'm just not used to being able to see any of your facial features, and that's what you actually look like underneath your beard all the time.
Can you repeat the blanks and the En plus portions? I don't completely understand what they are.
Great. Okay. Yeah, I'll just get rid of that, and we'll get rid of that. Okay. So if the value, so like we're basically defining it, we're okay. I think we're okay. We can understand. Let x be y, z. Right. We understand we understand the meaning of this expression. Right. The meaning of this expression is whatever the value of z is. Yeah. Okay. So I'm defining actually the value of a let block like this explicitly. We could define it to be whatever we want, but the typical definition is when you have a multiple let binding with multiple expressions in the body, that the value of this entire expression is whatever the value of En is. And the way to see this is to desugar this expression into syntactically allowable expressions whose value we agree upon. I mean, I'd already said what the value of this thing is by, this slide right here binds the value of the expression E1 to variable V, which can then be referenced in the expression E2, which is referred to as I guess I should, in the book it says, the value of this expression is the value of E2. Okay, there. Now you have it. Okay. Oops. Yeah. Yeah. Okay. So it's the value of this expression, whatever this expression happens to be. So I'm saying that the value of a let expression like this is the value of a final let expression whose body is EM. Okay. But in order to bind all of these variables, well, that's easy. We can deal with that. That part is easy, right? We let v1 be e1 in some context, and then we let v2 be e2 in some context, and then we let so on and so forth, all the way down to all the variables in the binding. But we still actually have to execute the body of all of these things. We have to do the operation, right? But we don't care about the return value, right? So we insert a little underscore, which is a gensim. We don't care. There's no variable name, actually, but we're going to generate a variable name so that it conforms to the syntax. And we say let underscore be en plus 1. And we go all the way up to em plus 1, which is to evaluate all of these expressions. And then finally, having done all of that, we can evaluate en. Now, if you're really thinking a step ahead, you would say, why would we ever do these things? Right? Because we've already said that we can think about this as pass by value, right? Which means that we should be able to basically, if we had no side effects, we could syntactically eliminate all of those expressions because they do nothing. But observe eventually is going to produce a side effect. So really, what these are here in place for, what they're here for, is if we want to put observes in those syntactic positions to produce side effects. And because Emma is worn out for whatever reason today and hasn't asked what is a side effect, okay? A side effect is going to be some, so the program is going to produce a value, I can tell. The program is going to have a value, but in the process of computing a value, if the computing the value of the expression changes the state of the world somehow, that's a side effect. If there's some change outside of the value of the program, that's a side effect. So I/O is a side effect because you do input and output, and that changes the state of the world. Tracking log probabilities, which is something we're going to do when we evaluate these programs. We're going to do non-standard evaluations of these programs which affect interpreter state. And this will become clear in 2 or 3 lectures, but there will be side effects that do extra things in order for us to actually computationally characterize posterior distributions, okay? Okay. So Namrata, did I cover your question clearly enough that you got it now? Cool, okay. So it makes it easier to write in the FOPPL. Actually, you'll find out if you decide to write programs in the FOPPL, it's actually not that bad. It's pretty reasonable, right? So here's an example sugared regression program. Note, if you remember before, this had a bunch of, let expressions here, which were really ugly, and made it actually, if you really look at this, kind of hard to read, particularly because of that, right? So instead, we can write something where we just say, okay, we have the slope, we have the intercept, and we just observe. We observe data. We call the observe data function multiple times inside a multiple let binding. So notice there's 2 let bindings here, and this, but we need to desugar that into a syntactically allowable form. Okay. Now you might also again ask, and there's a reason for going through this, particularly for your homeworks, because you're going to write evaluators in this language. You're going to write FOPPL evaluators, okay? But you're going to get programs with sugar. So you're going to see FOPPL programs that are sugared, but your evaluator will get desugared programs. So you could potentially get quite confused when you see the programs that you're going to operate on in the homework, and then you look at the JSON expressions that get emitted from the desugaring, the desugarer and compiler, which are in desugared form. So in other words, And why would we do this? Why do you want a simple set of expressions and forms? Is that your evaluator, at the end of the day, is only going to have to evaluate all of these forms. 1, 2, 3, 4, 5, 6, 7, 8. You will need to write 8 functions. Okay. And if you evaluate those functions correctly, then you will actually be able to reduce an expression to a value or a set of values or a computational characterization of a posterior distribution eventually. Okay. Additionally, like if you look at this, you'd say, oh my goodness, this is stupid. Why do you have to write down your data, like you're in, one line for every data point? Okay, well, okay, we can introduce looping sugar. Okay, so if you're familiar with TensorFlow or whatever, or I guess what's the other one? I'm going to ask Vasilios or Payman, the original one where they did
Theano.
Yeah, no, thank you.
Yeah.
So there are really strange loop constructs that you have to have if you want to have finite bounded looping. Okay, so FOPPL has really strange looping constructs that correspond to the same kind of thing, right? So for here we have a for each some constant value variable expression, but all the way to variable expression, and then some other expression e prime to ek. Okay, so what the heck does that mean? Who knows? Well, here's what it means. It means, definition from desugaring, it desugars to a vector whose first value is computed by or corresponds to this let block, where v1 is bound to get e1 0. So e1 is going to be some vector. Vn is get en 0. And then we evaluate all of the expressions e prime 1 to e prime k, and the value of the first element of the vector that corresponds to this loop construct is the value of e prime k, evaluated in the context where v1 to vn is bound to the first element of e1 to en. And so on and so forth. So the second one is get 1, and it's get all the way up to minus c1n, and so on and so forth. Okay?
I have a question.
Great. All right. Back to paying attention. Awesome.
Yes, sorry, I was very distracted. And maybe you said this when I was distracted and I totally missed it, but what does the get function do?
So I'm not sure.
Two arguments.
We did say that. So get is, as you will find out in the homework, a vector element accessor.
So it accesses the 0th element from E1?
Yep.
Okay.
Cool. Great question.
Can I also ask about like the desugared part? Because I see that like we have these E1 primes and like all the E primes, and they appear like multiple times in the desugared version.
Yep.
Like, I don't quite understand
Great.
why. Like I thought that those were like immutable or something. I don't know.
They're expressions. They're literally expressions.
Oh, okay.
So let me try to do an example here just really quickly off the top of my head. So let's do for each 2. And let's let v, we'll just have v, and we'll have vector 3, 4, and we will have times v. Okay, so this will get desugared to vector let v get vector 3, 4, 0. EK is times v, v. Let v get vector 3, 4, 1 times v, v. Okay, so you can think about desugaring as expression manipulation. And when you see E prime here and V, we really are saying take the expression, and this is referential transparency that I guess I missed in the chat from James, excuse me, sorry. Take the expression and just move it, copy it, right? So the expression is times VV, but V is bound to a different value that's dependent on the count. So ultimately, this then could be replaced with what? 9, 16. So these are all equivalent.
So this example helped. Can you give another example where we have like multiple expressions, like E1 prime and say an E2 prime?
Yes, there. I lied. That only has one. That only has one. Yeah, let me see. I don't think I have one here in the slides. But again, the only reason why you would ever want an expression other than the final expression is to affect a side effect. So the only time that you would ever put something in there like that would be if you had some other distribution and you wanted to observe under that normal, normal 1, 1 V. And if you did that, then in here, that would get desugared to observe normal 1, 1 V and observe normal 1, 1 V. The value of this is irrelevant. The side effect is not. And the side effect is something that will be computed. You'll understand the value of the reason for side effects when we talk about how the operational semantics for observe.
I have a question.
Naomi's turned off her camera to keep from being harassed. Yeah, okay. All right.
So the example that you wrote out was basically using this sugar form to vectorize the problem, and then desugared unvectorizes it? Or
no, so it's really so that you can write loops, so that you don't have to so if you notice the language itself had no loops. There was no looping. There's no looping construct in the language.
Okay.
Right, and there can't be a looping construct there can't be a general purpose looping construct in the language, because for an example that I think we'll give here in just I'll give it at some point. Yeah, so let me do for each, which is going to really confuse everybody, I think. Well, maybe not. Yeah, so the next one I'll drive home the point for why. No, wait, is this? Yeah, let me just do this here, right? Okay. So we'll just do this, right? So a general purpose looping construct would allow you to put here. So notice that this for each construct, right, takes a constant here. That's the requirement. It has to be a constant. If we allowed a general loop bound and we put an expression here, that would be really bad, right? Not least of which, and this is a less, this is a not terribly problematic, well, it is a terribly problematic example, right? So if we say, if we had the ability to write this, when should we terminate this loop? How many random variables are there in this program?
Very many.
There are potentially unboundedly many, right? This has support over, positive integers plus 0, right? Which means that this is an unknown quantity which could be infinite. So there could be an infinite number of normal random variables here.
So could you avoid that problem by specifying something in those square brackets after the for each m, and then?
No, remember this is a binding. So if there's nothing in here, there are no local bindings. So like for each, the definition of for each says these are bindings. So all we're saying here, just to keep it simple, is that in this particular case there are no bound variables. So this would just construct a vector of length m of normally distributed random variables. What's the length of this vector?
M.
Yes, which can be anything from 0 to infinity.
So, but you pick m.
No. M is stochastic here. M is a sample from a Poisson distribution.
Oh, m is from n. I see. Okay.
What if it's from like a Bernoulli though?
So again, that would be okay, but how do you know?
How do I know it's okay?
Yeah.
Because it can't take a value, and it has to take a finite value.
We have no type system.
Oh, I guess.
All
you just restrict it in the grammar.
All for each has is a variable name. What's the type of that variable name? And that variable name that could be, you can do whatever you want in order to construct that, right? So you could do like, Poisson n is a sample from a normal with mean q and variance y, and y is gamma something or other, and so on and so forth. So and q is normal 1,000,007. Now what's the type of m?
Well, I mean, you know the type of m, but you can't guarantee that it's not.
Okay, you know that, no, well, you you don't know the type of m because there's no type system. But even if you had a type system, you would still need to know what support that distribution has.
Yes. Yes.
Right.
So is there ever a situation where we would want to write something like this?
Oh boy.
Because I'm wondering, because the way that you're saying this is making me think, okay, either this is a problem with this language, and there's probably going to be another language that's introduced in the future that solves this problem. Because the way it just seems like it's not, or at least I don't know much about this at all, but it seems like it's a problem with the language being limiting.
Yes. Okay. Yes, I love it. Okay, great. For each data read file my data.csv. For each range data something. There's two problems. One is there could be an infinite number of random variables. The second one is this is sugar. So if you can't actually evaluate this expression in advance, you cannot possibly do this transformation. And if you can't do this transformation, you can't guarantee that the number of random variables is finite, which means that you cannot guarantee, as we will see, that the semantics of the program reduce to that of graphical models. And if you can't guarantee that the semantics of this program reduce to graphical models, then you can't run general purpose graphical model inference algorithms on the denoted programs. Right? So yes, it's a problem with the language, but another way of thinking about this is, wow, you guys figured out how to restrict a language so that you're guaranteed that any program you write corresponds to a graphical model, which means that you can safely write any program you want and guarantee that the general purpose inference algorithms that you're going to write in homework 3 will work for any program you write. Okay. So I think this is actually really super important. Like it's it seems stupid that we're looking at this highly restrictive language and why would we do it and blah blah blah. There's many reasons for doing it. One is to say that you're going to encounter prog languages when you're doing projects or when you're in the world or you're doing whatever that either don't actually explicitly that enforce this in really weird ways, and programming in them will drive you nuts until you realize that they have to be restricted in this way. So if you program in Stan or bugs or something like that, you're going to run into these restrictions and you're gonna be like, what the heck is going on? Why can't I just write a loop? This is dumb, right? And the reason is that you have to guarantee halting, right? And when you guarantee halting, then you can do graphical models and you can do all sorts of stuff, right? So that's one reason. And the other reason is, of course, is in fact that when we want to compile this to a representation whose meaning we agree on, which is going to be the representation of graphical models, then we're assured that there's a one-to-one mapping, basically. So we can actually place meanings on these programs, and as it will turn out, especially for the mathy amongst you, like writing down the meaning of higher order probabilistic programming languages was only done in the last year and a half, and new measure theoretic foundations had to be developed in order to even write down the meaning of such a program. Awesome. So cool. So now we can write the regression program in a different way, a way that might be more tolerable, and will, should make Ryan's eyes light up with understanding here in just a little bit, right? There's a reason I know what Ryan's research project is, and it has to do with compiling stuff, and he doesn't know how to write compilers yet. So let y values be a finite vector that's closed over by the program. We have a slope and an intercept. Note that this let block would get desugared, right? So you can start to see there's a lot of desugaring that's going to happen, right? In order to make this into something that only has the special forms of the FOPPL. Then this for each expression, for each 5. Note this is a constant. It's a constant. It is not a function of the length of y values or something like that. It's a constant, right? Please don't yawn, James. It's it's killer. So then we can say x is range 1 to 6, y is y values, right? So this is basically saying that the x values are 1 to 6, right? Integer valued, and then y is this vector. So at the end of the day, x is going to be bound to 0, 1, 2, 3, 4, 5, whatever, 1, 2, 3, 4, 5. Great, and this is going to be bound to y values, and then the desugaring of for each is going to do exactly what you'd expect. So x, get range 1 to 6, 0, get y values 0, let f of x be the slope and intersect, observe normal, blah, 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 and so on and so forth. So this basically says, now we have our data in a nice vector form, and we have looping constructs that allow us to ingest and condition on this data and compute functions and all sorts of stuff. Right? Now this isn't so bad because you can sort of imagine going one step beyond this. It's not really that hard to inline data that happens to be sitting in a CSV or something like that. Okay? And we just did this. And again, somebody needs to tell me that we need a pee break, because I keep thinking this class goes to 5:30 because I keep staying until 5:30. So like, we really should have an assigned, you know, Emma Hansen Memorial snack break. Everybody just eat and then take a snack break at the end of class. 22 minutes, you can handle it, right? Yeah. 2 minutes. 2 minutes to chew, okay? 2 minutes to chew, 3 minutes to chew, 4:41. See you at 4:41.
I have a question, Frank.
Yeah.
Okay, so if there's no typing, then how do we know that the thing we put there is a constant, in fact? And if we as programmers have to guarantee that, why can't we just know that whatever, like our expression maps to a finite set, so we're chill, we can just have an expression that like we know it's going to evaluate to a finite constant. So
there's a difference between runtime and compile time.
Yes.
Okay. So basically at the time when desugaring happens, so this is like this, I know why you're asking this question, and it's worth asking for everyone. At the time that compilation happens, if you can partially evaluate this expression, if there's an expression there instead, then at compile time, you have to be able to do it at compile time, then yes, you can do the desugaring. For sure. No issue. But you have to be able to do it at compile time, which means that, for instance, your data or whatever sizes or whatever have to actually be pre-specified. Otherwise, you're screwed.
I realize this is a little nitpicky, but you said it's an untyped language, but it seems like it's just duck typed.
Yeah.
Okay.
Would you like to explain what duck typed is to everyone?
I was going to ask what that was.
Yeah, I don't know that I know in super detail, but like Python is duck typed, where you know, you don't need to provide like the types of inputs to a function, but the type information is still stored somewhere. And then so things like, you know, adding a number to a string will still fail at some point because that doesn't make any sense. And so you still check the types. They're just usually held like as part of the value object.
So I would be careful here just a little bit. So when I hear duck type, I mean my understanding of that, and we should you know, Wikipedia to get the technical definition. I don't think there is a technical definition, but if there were, my understanding of it is basically a language whose type system consists of operators, primitive operators failing on bad inputs, right? So it's not really a type system, and there's nothing about this that says that you would carry type information around, right? At all, right? In your implementing language, because you'll be in Python, you probably will touch the Adam, what's your language? And Ryan, what's your language? You're going to do this in Julia. Then you'll probably carry around type information as you're going, for sure. And you might use that to prohibit doing bad operations, but it's not really any different, right?
Wikipedia says duck typing is an application of the duck test. If it walks like a duck and quacks like a duck, then it must be a duck.
Exactly, which is to say that if you try to add 7 and Donald Trump the string, it's going to fail. But if you, yeah, exactly, right. If you add 7 and 17, hey,
that probably works in Python.
That is the problem with Python. Yes. Okay. Anyway, fine. So there's some other loop sugar. So we have a actual loop construct, what really looks like a loop construct. This will make your eyes bleed a little bit. There's various reasons for why this is what it is. So there's some expressions E. There's another expression E and an expression F. Well, this is a user-defined procedure. So it basically allows you to get a count up. So this is basically the max loop index, 0 indexed. And there is the expression is the beginning of an accumulation. So 0, F applied to 0, and E and everything else. The 0th loop index applied to E and all of the values of the other expressions returns V0. V0 gets stuck here. It returns V1, so on and so forth. Really, it's more natural to look at examples of these and then think about what's going on. So here's a Gaussian mixture model, and it's actually pretty straightforward to read. So this says, let there be some data. So this is, again, a sugared let block, right? The likelihoods are for each 3. So we're going to repeat this 3 times and construct a vector. There are no bindings. Inside of this, we're going to sample a mean and a standard deviation, and then sample and then return a normal distribution object. Okay, this is a Bayesian Gaussian mixture model. So we have a prior on the parameters of the 3 mixture components. Then we have a discrete distribution, which is sampled from a Dirichlet distribution with uniform parameters. And then we have a distribution over the class variables, the class assignments. And then for each 7, which is of course the length of this data right here, we're going to bind the value of y to one of the elements of data and call the expression or evaluate the expression. Let z be a sample from the prior over class variables. Observe, get from the likelihoods. Note that this expression is defined in the context that it involves, that has a definition of likes, right? Yeah. So this expression evaluated here, likes gets expanded, get returns the zth value of the likelihood, which is itself a distribution object. So you observe under that distribution object the value y. And then this for each constructs a vector of all of the z's. The return value, so the posterior distribution in this program is over the joint class assignments of all variables in a Gaussian mixture model, in a Bayesian Gaussian mixture model, where you're integrating over uncertainty about the means, variances, and class assignments of the class assignment probability vector for all of the data points. So this, in a graphical modeling context, is hideously hairy. And again, to write down an inference algorithm for this is really not fun if you were going to do it homework 1 style. But by the time we're done with homework 3, done. You've got it. You will be able to do this no problem. Okay. Here's a hidden Markov model, same thing. Again, we have our data, we have a vector of transition distributions, we have a vector of likelihoods. Putting a prior on these things would be extremely straightforward, as you've already seen. The states are a sample from, again, a distribution. Sorry, this is the initial state vector, right? So this looping construct is a little bit like a counting reduce, for those of you who are familiar with reduce or fold, right? So it starts with the vector of states and then calls HMM step for each index with the accumulator states, and then the data transition distribution and likelihoods, which get dropped in place in all of these expressions. Okay, cool. There's a Bayesian neural network. Pretty straightforward to read. For each 10, for each 1, this constructs a 10 by 1 weight matrix. This constructs with a L2 norm prior. This constructs a 10 by 10 weight matrix from the same prior. A 1 by 10 matrix. B's, the offsets as well. Here's our data, which is a column vector of data, and then here's our outputs, which are 5 different outputs for the various inputs. Cool. There's a hidden layer. It's just exactly what you would expect from a neural network. Here's another hidden layer, and then there's a function for computing the mean of the output activation. Okay, and then you use for each constructs here, for each 5, for each 1, basically to loop over the data and observe under the normal under an L2 loss or an L2 norm the output from the neural network YRC given the input. Whew. Okay. Okay, cool. So this is the posterior distribution over all of the weights and biases in a neural network with weight decay and L2 norm loss. Payment's like, what? Really?
Yeah, where's the weight decay coming up? The L2 norm, I
right here.
Confused.
You put a prior on all the weights.
I see. Okay. Cool.
Okay. Oh, Emma's yawning too, not hiding it well. Oh man, it's rough. Were you yawning? Oh, God, I thought I got you. Okay. Anyway, so FOPPL take-homes. It's a simple language, which means really actually that writing an interpreter or evaluator for it is pretty straightforward. It's easy to deal with, right? And it's easier to reason about, maybe more importantly. We talked about sugar. That's an interesting concept from programming language, which makes the languages easier for humans to read, but you'll see. We've talked about I/O being forbidden because of potentially non-terminating streams, so we needed inline data, which is something that happens in bugs and stan and so on and so forth. If you remember from the bugs and stan example programs, the ones we saw, the data was actually just held separately, and there were methods for computing its size and computing and accessing elements of the data, basically binding values. This is the kind of language facility that you need when you want to make these restrictions. You should think of a FOPPL as an IR, not a production language. And the authors of the book and me, it's basically our attempt to define the biggest finite random variable cardinality language we could that actually looks like a programming language. So most of the other languages won't even have conditional structures like if. Okay, and they certainly aren't properly, their semantics aren't properly organized for the presence of that kind of branching. I'm going to point out that there is one even simpler language, and this is the first language that you'll probably write code to evaluate or interpret. So it is what we call the simple purely deterministic language. So you can think of it as a language consisting of FOPPL expressions that don't make any use of sample or observe special forms. And in fact, it doesn't have any let bindings or anything like that. So the language really is incredibly simple. They're constant values or primitive operations. They're variables. And the only expressions that are allowed are constant, variable, if recursion, or C recursion. By the way, this is also the language of neural networks. Okay, so this C, you should really just think that this C can be, again, very, very large matrix primitives and so on and so forth, and values in the language can be tensors. Okay, so this is, basically neural net language. A static computation graph. Okay, and more importantly, what you're going to do is you're going to find that after the compiler, in particular, when you look at the graphical model output, you're going to be left with expressions that are in this language. This is a subset of FOPPL, so evaluating expressions in this language will be easier than evaluating general FOPPL expressions. And the starter code that you have, I believe, evaluates this language. Is that correct, Baron? Yeah. So you are given a bunch of tests and a Python-based evaluator for this simple, purely deterministic language, which means you can evaluate link functions straight off the bat. Okay. So in the last little bit before I take the stream of interesting questions at the end, and Baron shows off the code, so I'll talk about this. This is important enough that I lifted these slides from a couple of lectures from now, and we'll go over them twice. Once before you do the homework, and once while you're in the middle of the homework. Okay. So evaluation or interpretation. So we've said that there are these expressions, and we've tried to talk about what they denote, right? But then we have to evaluate them somehow, right? We actually have to reduce them to values in some language that we agree upon. So what is evaluation or interpretation, right? So evaluation, in particular, eval, we're going to hear about eval as a function, right? Eval is a function that takes an expression and reduces it to a value, potentially causing side effects along the way. And again, the only side effects we'll have are random variable seed and whatever observed does, okay? For the time being. We have other ones later. An evaluator or interpreter for a programming language is a procedure that, when applied to an expression of the language or in the language, performs the actions required to evaluate that expression. So this is a mechanism for translating expressions in a language. And this, for non-computer scientists, of which there are, I think, many in this group, which is cool, right? And for the computer scientists who haven't written evaluators, this is really important, right? These are quotes, by the way, from Abelson and Sussman in the Structure and Interpretation of Computer Programs, which is, I believe, almost without question to be the most important computer science book ever, and well worth reading, whatever. It is no exaggeration to regard this as the most fundamental idea in programming. The evaluator, which determines the meaning of expressions in a programming language, is just another program. Okay.
Question.
Yeah.
Is an evaluator what provides the input-output functionality?
No. The evaluator is what takes the expression. Okay. Okay. Okay, Emma, what is the value of this expression?
10?
Okay, you were the evaluator.
Okay. Oh, it just runs it. Okay.
Doesn't just run. Okay, okay. We need to be very careful. Okay, and I'm not pedantic enough, but it doesn't run it.
It computes it.
It translates an expression. It determines the meaning of expression, right? So this is actually really important because you're going to write two, and this is actually the main point of the second homework, is you're going to write two different evaluators or interpreters for the same program. And in fact, the whole point of the course, the first part of the course, is that you're going to develop like you're going to write evaluators that do not look like running the program. Because if you think about running the program, there's no way that you're ever going to be able to do probabilistic programming inference. You'll never do inference, because the value of a probabilistic program expression is not running it. It's a computational characterization of the posterior distribution.
So where does running come in? Does it come in like at an outer level? Like, I'm just trying to map the knowledge I have about programming terms to what you're presenting here.
Running is a terrible, terrible misnomer, right? So there's compilation, which transforms an expression in one language to another. And then there's interpretation, which is roughly what you're referring to as running. But if you think about what a computer does, it evaluates expressions and produces values in some language that you're familiar with. Okay, just like you evaluate. This is some crazy string, right? Let A be 12. Let B, excuse me, be 13 times A B. That's a crazy string. But whoever's really good at mental arithmetic can get there quickly. I can't do 12 times 13. Maybe I should have made that 12. That makes it a little easier. Right? Okay. So there's this beautiful.
Sorry. Yeah. Can I just
Awesome.
ask? Yeah. So then, like the examples you show are like pretty simple. It's like multiplication, but how do you evaluate like observe and sample?
Oh yes. Now I feel like we're all like asking the leading questions that are going to bring us together as a group of people. Okay. So again, taken from SICP, we can skip over this because we'll get to this. Okay. So at the risk of confusing Emma, because this is going to look like running the program in the colloquial sense of running the program, we're going to spend a little bit of time. No, we have no time, so we can't do it. No, we're going to spend a little bit of time right now, and we're going to do this again. But I want to get it in front of you as soon as possible so that you can start thinking about the implementation of your program, so on and so forth. Okay. The implementation of homework too. So I hope, Berend, you can stick around long enough that I can finish this and you can still look at the homework. Okay. So this is in the program in the book, and you should be aware that you should be able to read this. I expect you to be able to read this, no problem. Okay. So row is going to be basically a hash map that consists of procedure names, F, and their bodies. Okay, so F is plus, 7x, and G maps to G of y maps to times y. And I'm terribly sorry, that I use simple examples, but it's only because they're like much shorter to write. Right? Okay, so this note, we're not going to talk about sample and observe right now. So we're going to talk about forward evaluation of the program. This is actually just straight computer science. This is writing an evaluator, an interpreter / whatever. Oh my goodness. Cool. All right. Cool. So let's look at what this does. So this is going to take an expression. No, I shouldn't have done that there. It's going to take an expression. What is an expression? It's any expression in the language. It's a program. Okay? And this is going to evaluate the program, which means it's going to reduce the program to a value in some language that we agree on the meaning of. Okay? So there's some expression. Okay? So what's the value of a constant expression? That's this case. It's the constant expression. It's the value of C, whatever that happens to be. Okay. Let's not do the next case first. Let's do this case. Okay. What's the value of a let expression? So in other words, we're matching the expression. So we're doing basically a string match on the expression, right? So if the expression has the form or can be identified as the form of let v1 e1 e0, then what do? Well, you recursively evaluate the value of e1. You determine the value of e1, the expression e1, and that returns some constant. Right? Then you bind the variable name v1 to the value c1, and you recursively evaluate the body of the let expression with a dictionary L with variable binding v1 pointing to the value c1. Okay. How about if? Pretty straightforward, right? So if you have an if expression, what would you expect to happen? Well, you evaluate E1, right? That's going to give you some other expression, E prime 1. In particular, that had better take, we could have called that a constant, doesn't really matter. It better take a Boolean expression. There's the duck typing, right? That's duck typing 101, right? If it walks like a Boolean and quacks like a Boolean, then it's a Boolean, right? So if E1, then return, oh, there we go. We're going to evaluate the consequent, E2, with variable bindings L. Or we're going to evaluate the alternative with variable bindings L. Okay, so again, same thing here. So now we have some function application. So what do? We evaluate all of the arguments with variable bindings L, right, to get values for all of the variable bindings. This is the pass by value thing that Payman can't hear because he's taking his headphones off. Too bad, he'll probably fail the course because of that. Okay, so then depending on what kind of thing E0 is, if it's a user-defined function, which we can determine by looking up whether or not f is in this global set of functions, that's the defin blocks above, what do? Well, we look up f in row, and we get the names of the variables, that would be this bit right here, and we get the expression which is its body. And then, having evaluated all the arguments to values, we bind all of the variable names for this function to those values, and then put them in the hash map of bound values, and then evaluate the body of the function with all the variable names bound. Otherwise, we just call the primitive procedure in whatever the underlying language is with the given values. Right? And of course, not terribly surprisingly, then we can go back to this case V, which just returns from the hash map the value of the binding for that variable. Okay. So this mutually recursive procedure, which almost certainly will cause some head scratching amongst a subset of you when you first look at it, and when you second look at it, when you third look at it, is an evaluator for the language. And this is, in the Emma Hansen style, a run it evaluator, okay? But that is not the end of the story for evaluating probabilistic programs, not by a long shot. But you need to understand how to write an evaluator like this in order to first evaluate the link functions in the purely deterministic language. Second, be able to write evaluation-based interpreters for probabilistic programming systems, which will get more complicated than this once we go to the FOPPL context, but this is the only way that we can do inference in the FOPPL context. But also to provide yourself a baseline against which you can compare an evaluator, which instead of doing this, actually compiles to a graphical model and then does operations in the graphical model. effectively just ancestral sampling in the graphical model while evaluating the link functions using something like this. I'm pointing at my iPad. I assume that doesn't make any sense if I don't know which screen I'm on your computer. So that's it. Graphical models correspond to and encode joint distributions. We did that before, right? We've got Markov blankets for Metropolis within GIMS, so we can look at graphical structures and automatically detect what variables we need to condition on and which parts of the program we need to evaluate. Link functions are usually redacted from graphical models, right? But those link functions are important, and we very, very explicitly represent them here, right? We now know that programming languages can be used to denote graphical models, or we'll see that very soon, if not now. We need to construct the language very, very carefully to ensure that all the first order language such that all the programs terminate and can only have a finite number of random variables. Sugar aids readability of examples, and we've done a first pass of evaluation. Look at that eval procedure, understand that eval procedure, and recognize that that's the primary thing that you will have to implement in homework 2. So the sooner you understand that eval procedure, the easier it will be to write homework 2, which does not involve inference, but instead involves, again, running the program. 2 different ways. Okay, cool. Thank you. Are there questions? And if not, then Baron can take you through if you have the time.
What's that sigma everywhere?
Okay, sigma, not surprisingly, is going to stand for something like a place where we can hold side effects. Okay, so for now, there are no side effects. There's nothing else that's being computed while you're running this program. But eventually, in particular, when we talk about this one, and depending on how far we go, this one, we will definitely start messing around with sigma. So in other words, be aware, and this is very smart to have noticed already, that the return value from this program, right, from this eval function is, yes, some base level of recursion. When this thing pops all the way out, there's going to be a value and some sigma thing, whatever that is, right? So there's actually a pair of values that's going to come out of this. We're really only talking about the value side right now. Soon enough, we're going to be talking about the side effect side. And that is when we're going to start talking about inference. More questions?
I have a question.
Yeah.
When we say to just sample the prior in homework 2,
yeah,
we're essentially just ignoring the observed case, as you did here.
Correct.
Okay.
Well, it's not just observing. It's not. So it's, yes, you're ignoring this case, but not ignoring this case.
Yep. Okay. Do we have to specify, like in our evaluator, we specify how many samples we take? Because these programs, we don't specify within these FOPPL programs how many samples we're generating. That's something external that we have to worry about.
Correct. So now you're talking about an approximate representation of the posterior or whatever distribution you're
Yes.
representing, right? And really, you want to think about a lazy forever sequence of samples. That's the representation we will use almost exclusively. So we talk about variational inference, and then it'll get a little confusing. But you'll see even there, you have to think about it as a lazy sequence of samples.
Okay.
So an infinite stream of samples. Baron, do you want to share your screen, and other people can ask questions while you're doing that?
Yep. If you allow me to share. Wait, sorry, I can actually do that. Never mind.
I was going to say
that's not the error message I got. And how much detail do you want me to go over this?
Don't show that repo, please. You show the code. In fact, hide that repo very quickly, particularly given how many people in the course are Bayman.
Okay,
don't take a screen capture. If you take a screen capture, you're going to fail the next one.
Then I have to find some other way to show you the code.
That is a no joke academic malfeasance straight away. Stay far away from the code, from the repo.
Oh, the code that I was showing on the repo was not the solution code.
I understand, but 1, 2, 3.
Oh, I see.
4, 5, 6.
Oh, I'm sorry. I see what I did now. I hadn't realized that. I'm sorry. Let me make sure that I'm not having the wrong code up on my end as well.
Yeah, for the record, I did delete whatever I did screenshot, and I just emptied the trash. So don't fire me, Frank.
Conveniently, that part of the lecture was recorded, so you know you've got to, you know. If it's problematic, I can just share it because I think I even have it up already.
No, I do now. Sorry, I hope that I have everything up. Okay, so the idea is that the files that you'll get are 5 files, 2 of which are the sort of.
I think that's. I don't mean to interrupt, but I think that's an underestimate of the number of files they're going to get.
Sorry, that's the number of code files. The number of actual files is a lot larger. So it's going to be a folder that includes some tests as well, but the number of code files will be 5.
Can you show them? Can you show them the directory structure?
Yeah, I can do that too. And I have to grab that as well. Sorry, guys. Too many windows open.
It's a good thing you didn't have an hour and a half to prepare for this, Baron.
Yeah. Well, I was just like, oh, Git does everything for me. You know, it's like the directory structure, all of this stuff. It's these big screens that are just not good enough for, or how do you say that? My current MacBook will just.
Yeah, I understand.
It's running a little slow. Can you see my screen now?
Yeah. Good.
Now, when I do this, then I hope that you can also see this directory structure.
Yes.
Good. So in here, you'll see these 5 code files. These 2, evaluation-based sampling and graph-based sampling, are meant to sort of hold your graph-based sampler and evaluation-based sampler. Then we have a file Daphne, which runs the compiler. We have a file with tests, which contains some functions for all the testing. So the way that this is set up is like all the infrastructure that you sort of need for testing is already in the code files. In principle, you don't need to do anything about that. And it'll just grab the tests and run them as you go. If you run into any problems with that, then let me know, because I was working very hard on this until the very last moment. So I hope that everything is okay. It worked fine for me. programs contains not only the 4 programs that you're asked to predict prior samples for, but it also contains tests which are subdivided into deterministic tests and probabilistic tests. So that's something that you might need to think about a little bit. But like, of course, for these programs, like if you ask it to sample from a Gaussian distribution, you're always going to get a different result. So there is some testing infrastructure to also check whether the samples you're producing are actually from a Gaussian distribution. And there's a few tests involving that as well. And they're all in probabilistic tests. Should I show a little bit of the code as well, Frank, or is that?
I think that's absolutely, that's that. You should show them like one of the deterministic and probably a couple of the deterministic tests as well when you show the code. But
yeah, so let's see. So the code here. Let's start with the graph-based sampling, because so the graph-based sampling is a little bit easier, and there's some stuff for you already filled out. So basically, what you're getting is a deterministic evaluator, which I think should work for most of it, but you might need to make a little bit of tweaks to it, but at least it should evaluate the most basic expressions that you can encounter. And you can sort of build your stuff off that, right? Then the function that you'll really need to complete is this function, sample from joint, given a graph. And then beside that, the rest is sort of for testing. There's another function here, which is one of the questions that came up earlier, is, like what is the return? Do you want one sample or do you want a stream? And you can actually see that this function will give you an infinite stream of samples from the graph that you're putting into it. And then these functions are for running both the tests, and then the main section is actually like running the deterministic test, but also the samples from the prior. Is that clear so far? Like any questions up until this point? Okay, I'm going to say that's a no. So the second one is evaluation-based sampling.
That's you need to take a longer pause so that the discomfort builds enough that eventually people overcome their tiredness and ask the question anyway, or Naomi stops chewing and then asks the question.
It felt like a really long pause to me, but I guess that's not so.
Yeah, that's the problem. There's like an invert, like the amount of pause and the feeling that associates that to it is like inversely proportional to the number of people. Like, when you're like a lecturer, like the more people there is, the longer you have. It's weird, yeah. Anyway, and it feels terrible as the lecturer. But yeah, keep going. Yeah.
All right. So for evaluation-based sampling, it's a very similar structure, but you're given a lot less. So this function needs to be completely filled out, and what that needs to do is take in a compilation result and sort of. I guess I can't say run in this case because we're just sampling from the prior. Is that fair? Or?
I think you can say that evaluate program there is exactly what we just covered on the last couple of slides. It's
okay.
Right. So okay. AST is an expression that's already been pre-parsed, and then you are writing eval.
That's right. So the rest of this file is very similar in structure. So you also have a function that makes it into a stream, which is useful for evaluating your probabilistic expressions. And then a function to run deterministic tests and a function to run probabilistic tests. Let's see. Something that I think is good to point out is that these paths that are to the test files, they're a little quirky because they are with respect to the Daphne compiler. And that's something that you might run into. So Daphne needs to be able to find them. And since this script is sort of calling Daphne, these paths that you're giving are not with respect to the script that you're seeing now, but with respect to the Daphne compiler. I hope that's also clear. But that's also, if you can't figure it out, then ask me, I can help. Which is probably a good time to take a look at this Daphne file. And the only thing that does is just invoke the compiler and pass the result back to you as a string. Sorry, as a JSON decoded objects. So some complex structure of lists and dictionaries. Still happy? Okay, so then the tests, so the test is kind of interesting because, as I said, like you want to see if some expression evaluates actually to a distribution. So feel like everything should work as it is, but also feel free to have a look in here and see how this is actually done. So the idea is that you just generate a bunch of samples and then check if those samples are actually from a distribution that you think they're coming from. So
using a traditional statistical hypothesis test based on cumulative distribution functions called the KS test. Yeah,
that's right. That's right. Yeah,
Kolmogorov, Smirnov. Somebody can correct my pronunciation. Test.
Yeah, I wanted to avoid pronouncing that, but
Kolmogorov, Smirnov. That's how I know it. But yeah.
Yeah. So the last file is a file with primitives, which I have. So this is actually something that I used while writing my evaluators because it was like the whole thing was just getting too messy otherwise. I don't, there's no requirement for you to use it, but I would encourage you to do that to keep your code a little organized. And I think that's all.
You have provided 0 primitives.
So well, yes and no. So okay, so if we go to graph-based sampling, what is already provided here is sort of like the environment primitives, normal and square root. So these are sort of natively implemented, so it's not that difficult. But for example, in the Bayesian neural net, the matmul and that sort of stuff, like you will need to construct those from tensor or from PyTorch primitives. Right. So these are trivial, and there's a 70% of them is trivial, but there are some that you will need to separately define as a function.
So this is what's known as a primitive procedure, right? And there's the primitive types and constants are basically data structure elements and string values from JSON. Right.
I have a question.
Yeah.
So FOPPL is implemented within a different, so it's not a language itself, it's a way of writing.
This is, you are going to find, honestly, I know that when you're done with this homework, you're going to find a level of satisfaction with computer science that you've never experienced before. It will actually make you happy in some sort of fundamental way. Mm-hmm. So all of you. So remember that an evaluator is a program that takes an expression and turns it into a value in an agreed language. So you can write an evaluator for any language in any other language. An evaluator is just a program. So in subsequent years, we've made you actually learn Clojure or other languages that nobody really actually wants to program in. This year, the work that we're doing is to transition over so that people can write the evaluators and that sort of stuff in, for instance, Python. So you can write programs in FOPPL, and in fact, can you show a couple of programs can you show the programs in FOPPL? So the .Daphne extension, so show one of the deterministic tests, and then like one of the homework problems, please.
Yes. Right, so that's the very first test.
So that is a FOPPL program that will be desugared for you and turned into a graphical representation with deterministic link functions in the first order language. These are 2 different representations by a Daphne compiler that Christian wrote a long time ago. That was homework 2 before, but like homework 2 in the last class was unbelievably hard. So like we're skipping over homework 2. If you want to look at homework 2, it's one of the extra homeworks, just for the fun of it. That's like write the compiler, right? What this is after you do the parsing, after you do the desugaring, after you do the compilation, now evaluate the program. Write an evaluator. Writing the evaluator is much, much easier. So this is, as Ina likes to make fun of me for writing very simple expressions on the slides, you still need to be able to evaluate this expression. But now can you go to one of the homework problems?
So let's just take this guy.
Okay. Your evaluator will also evaluate this program and any FOPPL program that you write. So you can write in FOPPL and then run a program, which would be like run. Your program could be called run. the Emerson naming convention for program run FOPPL program, and it will produce a result or stream of samples. Make sense? Yeah. It's fun. This is like, if you've, again, how many of you have written an interpreter? One. Mia, would you agree that it is one of the most satisfying things to see actually work when you get it? It's like, it completely is transformational in terms of your understanding of computer science. You cannot call yourself a computer scientist without having done this once. And to be fair, I didn't do this until I was a statistics professor after I was a statistics professor at Columbia and having gotten a degree in computer science as an undergraduate and as a PhD. So, but like, it was an absolute failure of mine to not do this because I didn't understand computer science until I did it at all. I had no idea what computer science was about. That's on camera, crap. But it's true.
I thought it was really fun. I really enjoyed this homework.
More questions, comments, worries?
Baron said that there's about 30% of the primitives that we have to implement.
No, you have to implement all the primitives, but if you're going to do it in Julia or you're going to do it in Python, basically, if you think about it, the primitives, you're doing it in such a powerful, you're going to be implementing the interpreter in such a powerful language that there's just basically going to be one-to-one correspondences between underlying functionality and primitives in FOPPL. So like implementing means write a hash map and maybe write 10 functions to, like make matmul do the right thing in your underlying language, right?
Okay, that makes sense, yeah.
Yeah. And I should say, just as a thing, I don't know if I wrote it, I think I did, but please do this in Python. If you're going to do this, do it in PyTorch, okay? If you're going to do it in Julia, do it in Flux, or I guess Julia doesn't really matter. Do it in one of the auto-diffable tensor computations. So make your base type not be scalars. Make your base type be tensors or auto-diffable objects.
To add to that, you will have trouble getting the testing to work if you do not do that.
So that's just looking forward to some of the crazy stuff that we'll do later on.
One other thing that might be useful to point out is that running a Daphne compiler, Frank knows more about this than I do, but it spins up a Java virtual machine and it does a bunch of stuff under the hood. So it ends up taking a bit of time. So you could consider compiling them to JSON and then reading those from disk instead of compiling every time over and over again. Is that?
Yeah, that's it. So yeah, indeed. So basically, if you saw that the Daphne compiler is invoked through a system call, and the Daphne compiler is a cloture compiler, and the cloture requires spinning up a JVM and then actually doing a bunch of just-in-time compilation of the entire cloture environment. So basically, every time you call the Daphne compiler, there's a 20-second or a 10-second spin-up time, and then like a 5 millisecond computation. Okay, so you can amortize over that by simply calling a Daphne compiler manually and constructing the tests to just actually consume JSON rather than FOPPL code. But it's written in a general purpose way right now. Just don't shoot yourself in the foot by like waiting for 35 minutes every time you want to run your tests, right?
I have more questions.
Good.
What if I don't know what PyTorch is?
Google is your friend.
Is there a large learning curve with PyTorch?
For what we're going to do, I think the learning curve will be just appropriate. It will be just fine. Basically, you can for our purposes, you can think of PyTorch as a mathematics library that operates on tensor-valued objects. So a scalar is going to be wrapped in basically it's going to be a zero-dimensional matrix or whatever, right? Or
So is it kind of just like it replaces NumPy?
Yeah.
Okay.
With some caveats, yeah. What it will give you later on, and why you don't want to do NumPy, is that you're going to get automatic differentiation out of it. And in later assignments, you will have, the later assignments will be very easy if you have automatic differentiation available to you, and almost impossible if you don't. So, yeah, I don't think you'll have a problem, certainly with this. Basically, it means make your primitive types be tensors, and make sure that you import PyTorch, and then operator overloading will basically give you everything else for free. And if you have any issues with that at all, I can definitely point you in the direction of Payman and Vasilios, probably Jason, probably Greg, probably Tony, all of them I know for sure. I don't know about the rest of you, I apologize, but certainly Vasilios and Payman, just ask. They'll they spend their lives in PyTorch.
Thanks.
And I'm guessing if people want to do, for whatever reason, so we've got Python bootstrapping, but I'm guessing that Adam for sure is going to do Julia, just based on early results. And Ryan, are you going to do Python or Julia for this?
For sure, Python.
Okay. Well, that's a strange choice given your research direction, but that's okay. Anyway, so if you want to do Julia, I'm guessing that Adam can lead that particular charge, because I'm guessing you're going to just stick with Julia.
Probably.
But we did not develop bootstrapping code for that, so.
I'll have to bootstrap myself.
It's not that bad. It really isn't. If you just look at what's going on in Python, it's really not bad. Okay. Anything else? It reminds me of. Let me see. I don't think I can find it right now. Let me give me 2 seconds, and then I'll leave you with this.
I have a question.
Great.
Do we have to evaluate like the underscores? Because we said that we don't care about those, but these are like this is very detailed question regarding the.
It's not a detailed question. It's a very good question. So what I said, if you caught it earlier, is that the Daphne compiler will desugar for you. So the net consequence of that is that you will never see an underscore.
Okay.
Yeah. Yes. So to quote from a review at Columbia, teaching review, and I suspect you're experiencing something like this. The assignments were challenging and probably the best part of the course. It was with bated breath and nervous anticipation, almost like a blind date with someone you knew would be pretty, that we waited for the homework. Okay, maybe that was 10% exaggerated, but yeah. So if something like that is happening right now, that would make me happy. Hello? Okay, you're always still there. Yeah. So that was a teaching review at Columbia. Hopefully, we'll get the same flavor of appreciation for the homeworks in this course sooner rather than later. Okay, thank you all very much. It was an honor and a privilege as always. Yeah, I'll see you next Tuesday.